Good morning. Here we go. All right, so really nice work on the test. I'd say pretty good average. I think, well, now off the top of my head, I think it was a great job. On test number 1. The average was 70.7%, I want to say, which I'm really pleased with. Typically the first test, because we cover so much weird material and we cover so much ground, the first test is usually the hardest. Right, especially because you're getting used to the course and getting used to the material, but also because we cover such a broad range of material on test 1, that usually makes it a little bit harder. And remember, when you look at your grade, I want to go through and adjust the grades. It's not I've got a couple of other things that are a little bit more time sensitive, so I've been putting it off for the weekend. So over the weekend, I'll go through and I'll just kind of make sure that if marks were taken off, then I'll just make sure that that's accurate. Okay, so I'll adjust the grades if there's anything that I find. But of course, I encourage you to go through and check your answers. And if you find something that you're kind of like, oh, okay, I'm not sure if that's actually wrong, then please send me an email. And then, so if you sent me an email right after the test, I've stockpiled those. I've put those to the side for when I go through and I look at the test. Okay, so if you're waiting for a response, then just hang tight, and I'm going to go through those when I go through the test, so then I can kind of be sort of organized, I guess, trying to be. So make sure that the test is out of 55, right? Because those last 3 marks were potential bonus marks. So test was out of 55, right? Not the 58 that it says. You want more time, huh? So the problem is, that was a good length test because it took me less than 20 minutes to do it. So even multiplying by 4, that's how much time you had. So usually I just multiply my time by 3, and that's how I do it. Yeah, and time flies, right? But the thing is, you shouldn't be looking up too much stuff. Right, you should know it. So that's why it probably felt a little bit long, but that's what we should be expecting, right? So that's why I said you have to move quickly through it, right? It's open book, but that can be a problem, right? Because then you feel like, oh, I've got it somewhere here, right? And so that can be tricky. So yeah. So I take my time, and then I multiply that by 3. Typically for this test, I multiply by 4. So that's why I feel like it was still a reasonable length. But yeah, the thing is, I do make sure that when I do my run through, I actually read all the questions, because otherwise, I've seen these questions so many times that that can speed me up, right? So I just make sure that I read everything and I do everything. But yeah, so I do use that as a benchmark. And I'd say for test 1, this is a really decent average, right? I know that that's a low-ish average. I think it's average of all the averages, which we'll talk about today. But right, just I think the average for the next test will be a little bit higher if you're feeling a little bit bogged down. So, okay, so I want to make a note here that if you emailed after the test, about the test, obviously. Oh, wait, I think I missed something. Oh, how many tests are we writing? Two tests. 2 tests. Should be in there, but yeah, it should be in there in the course outline. So 15% each. No, just one more test and then the final exam. Yeah. So if you emailed after the test, I will reply when I review all the test scores. Okay. So usually the reason that I am kind of vague with that 30% is because if you do better on test 2, then I'll shift some of that weight over to test 2. But if they're roughly the same, then I keep them kind of evenly distributed. But it kind of depends on how test 2 goes, and then I weight it to get you a higher grade overall. I want you to have high grades. I want you to come out of this with a good grade. I know how important that is. Yeah, so that's why I keep it kind of vague with the 30%, because then I can make adjustments. Test 2. So I'm kind of, yeah, you want to pass. I know that. Yeah. And so test 2, usually I'll have after, now let me see here. This one doesn't have the course or no, test 2 will focus on chapter 5, definitely 5 and 6. I want to say maybe even 7. Let me just check here. Let me just pull up the textbook. Where is it? Because they change things around on me. Yeah, so test 2 will be after chapter 7. Where are we here? Come back here. And so test 2 will be after we finish chapter 7. We'll only cover chapter 5, 6, and 7. Oh, did you guys see the final exam schedule is posted? Yeah, so, but then the final exam, of course, covers all the material that we have gone through. So if you Google Okanagan College final exam schedule, it'll just pop up. But our final exam, and maybe I'll put this in pink here, final exam schedule, we're on like the very last day-ish. I think it might be the last day. December 17th, and I guess not at, but from 9 to 12. Of course, it's online again because yeah, exams are always on your birthday. Yeah, that happens. If you've got a December birthday, yeah. Yeah, it's a 3-hour exam. That's pretty typical for, I think, all final exams, 3 hours. 3 hours of rigorous statistics. Yeah, what a way to start your birthday. Yeah, so yeah, and it will cover all chapters. I think we go now with the new, we're definitely gonna do chapter 8, and I'm just gonna leave it as cover all chapters. I'm not sure how deep into chapter 9 we'll get. Usually we don't get that deep into chapter 9, but I'll just keep it nice and vague. It'll cover all the chapters. 1 through 8 or 9. How about that? Okay, good. So, assignments. You probably did for the exam. I have no idea. 3 hours worth. This one was what, 26, 27 for an hour and a half, say 50 questions roughly. It depends on the questions, right? What we're going to find is that the questions that we just covered, those are pretty quick, right? And so then we can do quite a few questions. Whereas for the final exam, the stuff that we're going to get into now in chapter 5, 6, and 7, especially, those require a lot of time. So even just one little question usually takes about a page of work. And so then I can't ask as many questions, right? And so the number of questions is really not a good gauge. I could say it's 3 questions, but with 20 parts each. Rude. Right, and so 3 hours worth. Usually I make the exam about 2.5 hours in length, right? That's what I aim for. And then you have a little bit of a buffer room. Some multiple choice, yeah, of course. And then, so for test 2, you'll have to submit your written work, right? And so just be prepared that you're going to have to submit your written work, and then I'm going to check your written work. But there'll be a space to put your answer, but then I want to see all the work that went into it. Okay? So some multiple choice. Yeah. And, but a lot of written answers too, which leaves room for part marks, right? Which is hard with multiple choice. Yeah, so yeah, if you've done any sort of higher level math, you know, 1 page of work is not that much. So yeah, 4 pages, yeah, that's more like it. That's a question. We have to go through and prove it and show that you know what's going on, all that fun stuff. Okay, so, oh yeah, assignment. You've probably already done them, right? Assignments 5 and 6, because they were on the test, right? So are you submitting on Gradescope? Who told you about Gradescope? No, Gradescope is really awesome. I've used it in the past, but for this stuff, no, for test 2, you'll have to upload your work and the final exam. So I like Gradescope. I just feel like I should have gotten you guys to start using it right away. And so because we haven't, I'm just going to use a Moodle Dropbox. It's easier for you guys, and not for me, but for you guys. So here, just as a side note about the written work, so test 2, you will need to submit written work. And also for, I should say, for test 2, and the final exam. Okay, so yeah, so what I was saying was you probably have done them already because they were on the test, but assignments number 5 and 6 are due tomorrow at midnight. Yeah. Okay, good. I think that's all the, oh yeah, so how do you guys see the late passes? I like that you have them. You only get 2, but it's a really fun idea, right? So, but then when I go into my student version, I actually can't see how to redeem a late pass. So, yeah, so the late pass, you get 2 late passes, and you have to apply them before the due date, but then it extends it by 24 hours. But I actually can't see how you see it. So if anyone could let me know at some point, that would be good. Yeah. Yeah, no late passes for me. Yeah. Yeah. No, I want you guys to have the late passes. So I'm really happy that you have them. I just can't see what it looks like for you. So usually on, yeah, you see what you want to see. I will a late pass. Yeah, so, but when I switch my Moodle to student view, it doesn't show it to me. So that's kind of weird. But anyways, I'm glad you guys have them. And they're pretty cool, right? So, yeah, here you go. Have another 24 hours. It's okay. It's okay. All right. So let's start chapter 5. All right. So that's kind of that was just admin. Chapter 4 is distributions. Nope, because we did, so chapter or assignments 5 and 6 are from chapter 4, and they were already on test 1. These are on chapter 4. Chapter 5. Here we go. Are you guys ready? This is when we start the fun stuff. Inference. So chapter 5, and maybe I'll start this on a fresh page. It's that fun. Chapter 5 is, we're going to introduce the foundations of inference. Okay. And so And so usually, remember, I post those kind of notes so we don't have to write so much, but I don't have any notes for this section because they changed it. And this is a completely new way of introducing inference. And I love it. It's so good. And I feel really silly for not thinking of it myself. But it means that I don't have anything, ready to go quite yet, but that's okay. I love what they did with the revamp. So don't get me wrong. It's amazing. But yeah, so we're going to be writing out the notes, but of course, remember, I post them afterwards, so we're okay. I will steal some of the examples from the textbook because I want to show you there's some R code in there that I want to work through with you guys. And I posted it actually on the Moodle page already, but we'll walk through that together when we get there. Okay, so foundations of inference. Inference is basically why we're here. It's all of statistics pretty much, or at least it's the most important thing that we do in statistics. It's a really broad umbrella, okay? But in general, what we're trying to do with inference is we're trying to take sample information to infer something about the population, okay? And so just kind of generically, inference is when we take sample information Remember a sample, so sample information we can call a statistic, right? So a statistic to learn about the corresponding population information. The corresponding population information. And the population information is called a parameter. Okay. So we're collecting a sample and we're calculating something like the mean. That's pretty common, right? Or that's definitely common. But where we're going to start here is actually with a proportion, right? So 4 out of 5 dentists recommend, I don't know which one, Colgate. I should know. My husband is a dentist. I don't know. I don't know which one he recommends. I just buy whichever one's on sale and he puts up with it. Hey, if you married a dentist, should you have to pay for toothpaste? I'll bring it up with him. So anyways, things like that, right? So those would be proportions. So that's actually where we're going to start. Right. And so in general, there are kind of 2 branches. And then from those branches, we're gonna go through and look at different scenarios. But yeah, I'm just realizing how how unfair my toothpaste situation is. Yeah, so anyways, yeah, pretty funny. But that's a really common proportion that we kind of throw out there, right? So 4 out of 5, did they actually, yeah, a cook should get free meals. They should just be cooking for you all the time. That's right. Anyways, yeah. So some common parameters that we're going to try to learn about, right? And so what we're going to talk about is there are 2 main branches, or kind of, I want to avoid saying categories. Yeah, so there are two main types of inference. Okay, the first one that we're going to start with is proportions. Proportions, which is things like 61, I was going to write it as a fraction, but 61 out of 250 people surveyed said they use Colgate toothpaste, just to stay on kind of the same idea, right? And so here, this would be a sample proportion, right? So we take the sample proportion, but we don't care about just these 250 people. We're trying to learn about how many in the entire population use Colgate, or would say that they use Colgate, right? And so we have the sample proportion, and we're trying to learn about the population proportion, right? So we have a sample proportion. And then we're going to do some inference to learn about the population proportion. Now we're going to need some notation here, right? So the sample proportion is going to be denoted by a p hat. Okay. Or if you're old like me and you know what pH fat is, then it makes it really funny. I think it's like old school slang for pretty hot and tempting. Anyways, it's like really, really old. But anyways, pH fat, it's a thing. You can look it up. It'll be on Urban Dictionary, but like Urban Legend Dictionary. So p hat is the sample proportion. And what we're trying to learn about is the population proportion. And you might remember from way back when we said population stuff, right? So parameters, we usually use Greek letters. This is the one exception where we don't. We use P. Okay, so just as a note, we typically use Greek letters for parameters. We typically use Greek letters, and maybe I should capitalize the Greek, let's not be rude. Greek letters for parameters. Okay. Yeah, like mu and sigma, right? And so we could use pi, which is the Greek letter P, but pi has its own meaning, so we avoid it, right? And so we could use pi, right? But it gets confusing because there's that irrational constant pi, and so we don't want to be messing around with that, right? And so but to avoid confusion or potentially introduce confusion, depending on how you feel about it, but to avoid confusion, we use P for a population proportion. Okay. So this is where we're going to start. Okay. And we're going to start with a single proportion, and then we're going to be comparing two sample proportions to each other, okay? And then, so there's kind of more scenarios that fall out of mu and sigma that fall out of the proportion kind of branch, okay? And then the other main branch that we have is for the mean, okay? And so there are two main types. So I guess here, the first one we'll say is the proportions. And so 2 is for means. An example would be the average commuting time is 45 minutes, right? And so the average commuting time, oops, for 62, I don't know why I'm sticking with these. Let's just go for 47. I don't know. For 47 commuters, is 27 minutes. So again, right here, I have a sample of 47 commuters. That's not all commuters at all, right? But it's a sample of commuters, and I have the sample average, okay? And so kind of similar idea here, we have the sample mean, and then we apply some inference to try to learn about the population mean. Same idea here. We already know what the sample mean notation is. It's X bar, and the population mean notation is mu, right? So here we stuck with that just in general, right? We use Greek letters for populations. And so we take X bar, we take the sample mean to try to learn about the population mean. If we go back to the population proportion, although it applies in both situations, to know what the population parameter is, right? Whether it be proportions or means, we would need to collect the entire population. But that's not feasible, right? No one wants to do that, and there's no reason to, right? And so that's why we've developed this inference. Now, I say inference generically because there are many things that we could do within the realm of inference. The most common things, again, that we're going to focus on are confidence intervals and hypothesis testing. So the two main, and I say main because I can't think of anything else, but I'm just leaving it open to potentially some other things, but I can really only think of two things that we can do. But the two main, you know what? I'm ready to commit. The two branches of inference are confidence intervals and hypothesis testing. So what we're going to do in this chapter is we're going to, so a confidence interval helps us figure out where the population parameter might be, okay? So it gives us an interval of where the parameter might be. Okay, so it kind of helps us pinpoint where this population parameter might be. Remember, we don't actually know where it is because we haven't collected the entire population, right? And so that makes it difficult. But based off of our sample, right, we know that our sample population or our sample statistic, for example, a proportion, right? Our sample proportion should be similar to our population proportion. Not necessarily the same, but similar, right? And so we can use that population proportion to learn about the population. Can use the sample proportion to learn about the population proportion. Too many P's, parameters, proportions. And so, so it gives us, so the confidence interval gives us an idea of where this population parameter might be. Whereas hypothesis testing, it lets us establish significance. Okay, so here, I'm going to try to keep it on the same page here. Okay, so hypothesis testing, yeah, p-values eventually, right? And so there's p's everywhere. You gotta keep them straight. Parameters, proportions, populations. All right. So in general, there's these two branches of inference. So in this chapter, we're gonna kind of just roll out all the ins and outs of confidence intervals, hypothesis testing. But before we can do that, we need to introduce just some of the ideas that we're going to be using. So section 5.1, hey, this wasn't even a section. I know this was just like the preamble introducing all the things. So section 5.1, I think I have it here. I just jotted down some notes, is on point estimates and sampling variability. Okay. Sampling variability, you might have seen I posted, on Moodle, I called it the central limit theorem because I couldn't remember what the section was called, but I know the general idea is the central limit theorem. And so here, so that's where I want to get to today. If I can remember when we go till, I think we're good. Okay, still have time. So I'm going to call it the central limit theorem. And what's neat about the central limit theorem is that it doesn't just apply to proportions like we're going to see. It actually applies to many other distributions. In fact, we've already seen it for the binomial distribution, right? Remember when we use the normal approximation to the binomial, right? And so we've seen this before. So let's introduce some stuff. So what we call, let's first talk about the point estimate. Okay, so the point estimate is going to be, in general, it's going to be the sample information. Right, so in general, right, it's going to be either p hat or x bar, right? For now, it's going to be the p hat, the sample proportion. So you can see how important it is to really solidify all that notation, right? P hat is the sample proportion. And maybe I'll make this a nicer hat. There. Right, so the point estimate is going to be the sample information. So what we're going to have is we're going to build up to some distribution of P hat. So, and later some distribution of X bar. So just as a reminder, because it's going to be important, lowercase n is the sample size. Right? Well, no, so when you calculate the sample mean to learn about the population, that's inference in general. So there's going to be calculations involved where we calculate the confidence interval. And so a confidence interval is a type of inference, but we could also end up doing hypothesis testing, if that helps. Awesome. Okay, so just as a reminder, we use a lowercase n to denote the sample size. And what we're going to find is that our estimate, right, so our point estimate actually becomes stronger and more like the population parameter the larger our sample size is. Okay. And so we will find that as n increases, the point estimate will approach the parameter. The parameter, it's estimating, right? It's a point estimate. So the sample proportion is a point estimate because it's trying to estimate the population proportion. The parameter, it is estimating. Right, so what we could say is that P hat is going to approach P, right, as the sample size increases, as n increases. Why is that? Well, my sample proportion, as I increase my n, right, as I increase my sample size, then I'm eventually going to end up at the population proportion, right? If I've taken a large enough sample at the entire population, in fact, then my sample proportion is my parameter, right? It is my population proportion if I've sampled the whole population. That's not going to be true, but what we're going to find is that we get more stable estimates as we increase our sample size. Okay. So the difference between the sample proportion and the population proportion, we can kind of categorize those differences in two ways. So there's going to be sampling error, right? Not really. So the question was, can you move backwards? Does it work? Does the population proportion approach the sample proportion as you decrease n? Not really, because we don't move that way. Because we'll never actually start with the population information. I'm not sure if that helped or hindered. But no, the short answer is no, it only goes this way. Okay. I guess in theory it would go the other way, but no, we're only going to go from the sample proportion to the population proportion. Oh yeah, and so the difference you could, so what you're kind of leaning into is called Bayesian Statistics, but we're going to use a frequentist approach. So if that doesn't mean anything to you, then you can ignore that. But if you've heard of Bayesian and frequentist statistics, that's sort of what Bayesians do. But I'm not a Bayesian, I'm a frequentist, and so is most other people. And so you're all going to be frequentists. I'm going to make you frequentists. And then I'll force it down your throats. But if you do keep going in stats, then yeah, all the cool kids are Bayesians, and yeah, anyways. But you're here with me. I'm going to drag you down. No, it's a Bayesian frequentist. That's going to be tricky. Yeah. Anyways, but it's good to know that there's kind of these two approaches that we can do. So typically statistics is introduced through a frequentist view because it's easier to wrap our heads around. Right, and so we take sample information, right? We've collected sample information, and then we try to learn about the population. That's what we're doing. So Bayesians, in a nutshell, they go in and they say, oh, I think the population looks like this, and then they make adjustments looking at the sample, and then they eventually end up at what the population looks like. So it's a little bit different, a little bit harder to wrap your head around. If the sample size is decreased, yeah, so I mean, the sample is a smaller version of the population, right? So we have decreased it, but we're only interested in, so this is from the chat here, so, but we're only interested in this direction, right? From the sample proportion going to the population proportion. Because we can know, so the thing is, if we've collected a sample, I know everything about that sample. Right? I can calculate anything I want. I can look at anything I want. I know everything about the sample. Whereas I don't know anything about the population. I'm trying to learn about the population. So I take everything that I do know from the sample, and then I apply it, and I put some error bounds on the sample information that I have to try to learn about what the population might look like. And I think that should address the question. Awesome. So the difference between, yeah, bias, good. So the difference between, between P hat and P is the result of two things. The first thing is the sampling error, or rather uncertainty. We typically use error to kind of lump all that uncertainty in one place, right? But error makes it sound like it's wrong, right? It's not necessarily wrong. It's just how different is the sample proportion from the population proportion. We've seen that before, right? Where we said, okay, when I buy a bag of chips, I know that it doesn't weigh exactly as much as it says on the bag, right? It should weigh around that, right? And so this is the same idea. We have our sample proportion, and we understand that it should be similar to the population proportion, but it's not exactly the same, right? And so the difference comes from the sampling error or the sampling uncertainty, right? And then the other source of the differences is the bias, okay? And so is bias, which if we just have a quick little reminder, bias is a systematic tendency to over or underestimate the population value. So if we've taken a sample from a group that doesn't represent the population, then that would result in bias, right? But it's also sampling error. So they go hand in hand. So bias is a systematic tendency. Oh, whoops. Tendency to over or underestimate the true, oops, I combined it to one word, the true population value. Okay. These two are very closely related, right? Because if I have sampling error, or sampling uncertainty, so if I'm just taking a portion of the population and I'm using that, even if it's randomly selected, right, that would be chalked up to uncertainty because I haven't looked at the entire population. Whereas the bias would be if I'm looking at a group that's not representative of the population, right? And so if our sample is not representative, oops, I don't know why I ended the bracket there, but of the population. So remember, the sampling error is the variability within the sample. Yes, but what we mean here is, so the sampling error is just because we're not looking at the entire population, there's going to be some differences there. So maybe what I'll do is I'll bump this down, give myself some room here, and we'll talk about sampling error in more detail. Oops. The sampling error, whoops. Trying to figure out there, that's where it came from. So the sampling error is because we're not looking at the entire population, right? So since we are not looking at the entire population, we understand that even a representative sample will have different values for things like the mean and the standard deviation or the sample proportion, right? So since we're not looking at the entire population, we understand that even a representative sample will be slightly different from the population, right? Will be slightly different than the population. Okay. So the difference here is the sampling error or the uncertainty, and that's why I kind of prefer uncertainty here instead of error. But the sampling error is even if we have that even a representative sample, right? So even if you have a representative sample, and let's just go back and remind ourselves that the best way to have a representative sample, or the only way to have a representative sample, is if the sample is randomly selected. Okay, so that's going to come into play. And so here, oops, that should say selected. Okay. So even if we have a randomly selected sample, which would be representative or considered representative of the population, we understand that the sample information is going to be slightly different from the population. Whereas if we're introducing bias, or if we're talking about bias, right, then we have this systematic tendency to over or underestimate, right? And so if our sample is not representative of the population, which means not randomly selected, that is not randomly selected, and you can see how all these definitions all come into play. What's the definition of being randomly selected? Means that every individual in the population has the same probability of being selected, right? And so that's from test 1, but you can see how it's coming into play here. In fact, it might be worthwhile putting it down again. What's the definition of randomly selected? Every individual in the population has the same probability of being selected into the sample. So every individual in the population has the same probability of being selected into the sample, right? And so that's the definition of a randomly selected sample, is that every individual has to have the same probability of being selected. Now, we understand that that's really hard to do, but if we can't make that happen, then we need to deal with this bias, right? And so that's going to be contributing to how far off our sample proportion is from our population proportion, right? So these are big ideas, right? And it's going to take time. What's really nice though is we're going to introduce these ideas in this chapter, and then we cycle through them one more time in chapter 6, and then we cycle through them one more time in chapter 7. Okay, so this first time that we see all this stuff, it's gonna be a lot, right? It's overwhelming. It's a lot, but just take comfort in knowing that, okay, we're gonna do another pass through this, right? And so I always struggle with, do I introduce all the things to you all at once and tell you all the ins and outs and all the nitpicky things, and then we just go through it again and then it becomes easier? That tends to be what I do. Some other people will just do a quick introduction of everything and then fill in the gaps. But I actually like, so for me personally as a learner, I like to see everything and then go through it a couple more times. And so that's what we're going to do. But if you just pick up some key concepts from this chapter, just rest assured we will go through it 2 more times, okay, just with slightly different changes, right? So slightly different scenarios. For example, we're going to start by talking about 1 proportion. Then we move on to 2 proportions. How do we compare 2 proportions? The same rules apply though, so that's nice. And then we move on to 1 sample mean. And then we can compare 2 means. There's a couple of different ways that we can do that. And then we can move on to multiple means, right? And so we can kind of build this library that we have. So I guess what I'm trying to say is if it doesn't make sense the first time, it'll hopefully start to make sense second or the third time, right? And we'll get there. But what I do is I'll give you kind of a framework, right? So even if you're not quite understanding, you can still use these kind of store-bought sentences, for example, or I don't know, to kind of think of it in a fun way. So I've got these pre-packaged kind of conclusions and things that you can use until it starts to make sense, right? And then so hopefully we'll use those training wheels, but then eventually you'll start to kind of come up with these things on your own. Okay, so one thing that we need in order to do any sort of inference is what we call the sampling distribution. Okay. So to do inference, I should do inference. It sounds weird to me because we haven't talked about it, but in general, we're going to do inference. So to do inference, we need to first introduce the sampling distribution. We need to first introduce the sampling distribution. Now, these 2 words, we probably know these 2 words individually. We know what sampling is. That's when I take a sample, right? And I know what a distribution is. It's when I look at my data and I look at the shape of the data, right? And so here, this is collect data. And this is the shape of the data. Here's where it gets a little bit weird. So what we're going to find, or the idea behind what we're going to talk about rather, is this idea of, okay, so if I took a sample, so if we start by saying I took a sample of 100 people, then we say, okay, but in theory, if you took 10,000 samples of 100 people, then how many would say yes, right? If that's what we're looking at. Okay, and so it becomes a little bit tricky, but to introduce this, I'm gonna steal the example from the textbook because I wanna use I wanna show you that R code that's in the textbook as well. So we have to introduce the question. And so here, I'm going to steal this whole section. So that we can talk about it. So what I want to make a note of here, first things first. So we'll just read the question together. So suppose the proportion of American adults who support the expansion of solar energy is P, which is 0.88. Now notice in this scenario, we're assuming that we know the population parameter P. So here, assuming, assuming we know the parameter already. This is just to illustrate the sampling distribution. Okay. This is just to illustrate the sampling distribution. So that's not going to be the case anymore, right? And so here we're assuming that we know that the population proportion is 0.88, right? And so, which is our parameter of interest. Now there's a little footnote here, and it's probably saying the exact same thing that I'm saying, because usually we're trying to figure out what P is, right? But now we're going to start by showing that it works out, that we can find P by taking a sample. But, right, and so if we were to take a poll of 1,000 American adults on this topic, the estimate would not be perfect, but how close could we expect that sample proportion in the poll to be to 88%? One side note that I'm going to make here is that for proportions, we need to keep track of the percentages, because eventually we're going to find probabilities associated with proportions. Probabilities can also be read as percentages, so that can get confusing, right? So here, how do I note? When we deal with proportions, we often report percentages. Okay, this can get confusing when we're trying to find probabilities, because remember, proportions, probabilities, and percentages, they're all basically the same thing, right? And so we often report percentages, and this can get confusing when we start talking about finding probabilities associated with proportions. When we start talking about probabilities, right, associated with proportions, since probabilities are often also reported as percentages. Okay. Since probabilities are often also reported as percentages. Okay. That's something to keep in mind. And we'll see in the example that we need to really keep these straight. And I think there's another example that I want to do. Hopefully today we'll see. But so, and this looks like repost, but it should be report there. Okay, so we need to really keep those straight. And my only advice to you is just really read things carefully. It should be obvious which percentage it's referring to, but just keep it in mind. Okay. So what we can do we want to understand, how does the sample proportion p hat behave when the true population proportion is 0.88? So this is kind of the reverse that you guys were asking about before, right? We start and we say, okay, what if I know that the population proportion is 0.88? How close can my p hat get? So we can simulate responses we would get from a random sample of 1,000 American adults, right? This is only possible because we know the population proportion is 0.88. That's not necessarily the case later on, right? And it's actually definitely not the case later on, because we're going to try to guess what this 0.88 is, right? But we start going the other way. So what we can do is we can construct a simulation. And that's that R code that I've posted on Moodle. And what I'm going to do is, because I'm running kind of low on time today, is I'll save that for tomorrow morning and we'll work through it together, right? But you can have a look before then. So what we're going to do is there were about 250 million American adults in 2018. So what we could do, in theory, we're not going to do it, right? No one wants to do it. But on 250 million pieces of paper, you could write support on 88% of them and not on the other 12%, right? You could generate the population, okay? Then you mix those up and you randomly select 1,000 pieces, okay? And then we count how many were in support and how many said no, right? Then it gets kind of funny. Any volunteers to conduct this simulation? Probably not. 250 million pieces of paper. Yikes. Think of all the death by 1,000 paper cuts, right? That's the saying. And so running this simulation with 250 million pieces of paper would be time consuming and very costly, right? But we can simulate it using computer code. I feel like should be the computer code posted on Moodle. Okay. So we can compute this. We can pretend that this is what's happening. So imagine you've got this bucket of 250 million pieces of paper. It would probably have to be more like a shipping container, but still, even if they're like this big, I don't know. And then, so, okay, you take 1,000, you randomly select 1,000 pieces of paper, great. What if I tell you, okay, now do that 100 times, right? As if once wasn't enough. So, but computers can easily do that for us. And I've generated an example that we'll go through. But for now, let's just talk about the results of that example. So, hey, code, it was a good guess for the final word. And so here, I changed because when I copied this code into my R code, it actually didn't show the underscores. So I changed the variable names, that's fine. But just as a heads up, if you're trying to copy this, it didn't generate the underscores, but I posted the code on our Moodle page. So what we can do is, and we'll save this, we'll parking lot this for tomorrow morning. What a way to start the morning, right? And so here we can make the computer do the simulation. In fact, what they don't show is one simulation isn't really enough to understand what the distribution is of these sample proportions, right? And so what we're going to find is that we're going to have the sampling distribution. So if we do this, 1,000 times or even just 100 times, we'd have a sample of sample proportions. Okay. And so we can run this simulation 100 times. Okay. And then we would have a collection, we would have a new sample of 100 sample proportions. And we would get a sample of 100 sample proportions. Okay. So this, a sample of 100 sample proportions, that's where we get our sampling distribution. Okay. This will be our sampling distribution. It gets a little bit tricky to think about because we're taking, so if we're taking a sample of 1,000, so remember our big, let's think of it as a bowl of paper with yes and no, you are replacing. Yeah. So everyone's randomly selected. Doesn't really matter as long as your population is large enough. So let's say no, you're not replacing people each time. I'm taking it back. You don't. So once someone's in the sample, because we're not bootstrapping, we're just pulling them out. Once they're in the sample, then they're in the sample, right? And so they're not going back in to potentially be picked twice. So without replacement, final answer. So what we do is we collect a sample of 1,000 pieces of paper, and then we record how many said yes and how many said no. From there, we can get our sample proportion, right? Then we put all those 1,000 people back into the pieces of paper back into the bowl. And then we collect a new sample of 1,000 people. And then we do, or people, pieces of paper, it doesn't matter. We do that 100 times, which means that we're going to have a new list of 100 sample proportions. Once we have a sample size of 100, we can visualize that, right? We can look at the shape, the center, and the spread. And what's really cool is we're going to get a normal distribution. We will find the sampling distribution follows a normal distribution, is approximately normal. And I'll end it there because I'm out of time, but that's a really, really cool thing. So now we're going to have a normal distribution. As soon as we have a normal distribution, right, a bunch of things open up, right? As soon as we have a mean and a standard deviation, which we will, then we can use what? We can use the Z table to find probabilities, right? Or we can use Z scores to find probabilities associated with these sample proportions, right? And so that's where we're going to kind of everything busts open and we have all these tools to use. But I'll leave it there. And then we'll start with the simulation tomorrow morning, and then we'll keep talking about this. If you have any questions, let me know. Otherwise, I'll see you tomorrow morning. I'll end this.